For those of you not in class today, I decided to record PowerPoint so you can take a look at it in the comfort of your own homes. Today, after exercise 15, we reviewed the 4 fundamental concepts of statistics. Basically, this is a link between what we did today was we linked all the work we did previously to inferential statistics, as you'll see. First of all, up till now, when we looked at a data set, we assumed it's all the data we had and it represented everybody who was responding. Occasionally, we did refer to the fact that this was a sample from a population. In most research, we don't take and measure every single person in the population that we're interested in. And that is what sampling is all about. Then once we have information about the sample, we can make inferences from the sample to the population. So this flowchart, if you watch the previous video that I posted, you have seen this already, and so you know this is there are individuals in the population, and those individuals are the ones that not every individual within the populations can be selected for the data set. Okay, and so you can look back at that video to get more on this. In exercise 15, what we did is we had a series of dice rolls. So everybody in the class, everybody who comes to class today will roll dice, and we're going to take samples of 6 rolls of the dice. So person 1, so this is sample 1, this is sample 2, this is sample 32, etc. We're going to keep sampling. Once we create these samples, from each sample we're going to get a mean for the number of dice. So you can see here we got a 2, 3, 4, and we get an X bar. So sample mean 1. Sample mean 2, sorry, this is sample mean 5, so let me just, this is not 32 here, let me just cross that off. This is 5, right? So this is a 5 here, that's for sample mean 5, and so on. We keep sampling. And so each of these samples will now become part of a new distribution called the distribution of sample means. So we did that in class today. And that is the link between data sets. So this data set, so this is like your data set, this is a sample from a population, and it's going to become an individual score from a distribution. You might have to think about that for a minute. Here's some symbols you'll have to know. So both of these are means, but this is a sample mean versus a population mean. Very important distinction. Same thing, S is a sample standard deviation, and sigma is a population standard deviation. Memorize these. Random sampling. In order to be able to make valid inferences about a population, comma, sampling must be done randomly. To choose a sample randomly means each of the following 3. Every member has an equal chance of being chosen, so you have to organize the sampling so that happens. Each individual is chosen independently of the one before or the one after. All combinations, even the weirdest ones, are possible. Sampling frame. So we're going to call that target population. That's a little bit different than the printout you have. This is the physical representation of the population from which the sample is chosen. So if we go back here, that's this. So that's the physical representation of all the dice rolls. And that's where we're taking a sample from. So it could be, for example, George Brown. It could be George Brown students. Or it could be George Brown students at the waterfront campus. Right? And every time you change the boundaries, you change the target population. So it could be a list of names, and it could be a description of the boundary, as I just mentioned. Sampling error. We know that each sample contains only a fraction of the population. That's the whole point. Infinite number of samples is possible. So every time you take a sample, it could be a little bit different result. Most samples will approximate the population, but they will all contain some error. So I did talk about that in the previous video as well. i.e., x bar does not equal mu. So x bar is the sample mean, mu is the population mean. The error, the difference between x bar and mu, is called the sampling error. And it'll be, depending on the samples, the error is going to be different. So it also has a distribution. Imagine researcher is able to keep taking samples. So that's what we do in class a little bit. We'll have 30 or something today, but we could have had 60 or 55 or whatever it was. And we'll create a series of sample means. So x bar 1, x bar 2, x bar 3. So that's where you saw the series of 6 rows. Each one was a sample. The collected and ordered data set, all those sample means, is called a distribution. The distribution of sample means. Remember, sample means x bar 1, x bar 2, etc. And so we're back to this drawing again. Each sample mean is one sample from an infinite possibility of sample means. So we can keep sampling an infinite bunch of times, and each we're going to have these dots, dot, 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 dot. Each one is a separate sample mean. And you can see where we're going with this. We're going to create a normal distribution. Shift from population distribution, right? So population distribution is raw scores, where our x, and to a raw score of x bar. There should be a bar there above the x. And so we have, this is what actually happens. We have the mean mu here. The mean of the distribution of sample means is also mu. Standard deviation is sigma. Instead of standard deviation here, we have standard error, which is estimated by s over root n. There's a lot of mathematics under the hood here that you don't have to worry about. Moving from z tables to t tables, a z score relates a raw score, right, x, to the population distribution with a population mean mu. The t-score, so we're moving from z-score is a population distribution, t-score is a distribution of sample means. Right? So that's what is going on here. So when we're dealing with samples, we got to deal with t-scores. When we're dealing with the population, when we have the whole population, we can do z-scores. T-tables adjust to various sample sizes, degrees, what's called degrees of freedom, which is a sample size, which is little n minus 1. Higher the sample size, the closer the distribution is to the z-table. That's just a fact. Central limit theorem tells us, and this is something that, again, each of these is an area where you're going to have to do some thinking. Population has mean mu and standard deviation sigma, then the distribution of sample means will have mean mu and standard deviation sigma over root n. Right? So as the sample size gets larger, the standard error is going to get smaller and smaller. So here's the formulas, z-score formula, t-score formula. You can see how they're so similar. X minus mu, we have x bar minus mu. And then where we have the standard deviation sigma, we have the standard error, which is an estimate for sigma. X bar, these are sample means. Right? X bar 1, X bar 2, with M as the symbol used instead of X bar. Now what we see here is that if you recall, this is S over root n, or sigma over root n, which is the standard error. And what's the relation between sampling error and the confidence interval? Well, essentially, when we're taking a sample, we calculate the mean to get X bar 1 or 2 or whatever it is. We get heights of 167, that's fine. Is that mean, i.e. X bar 1, equal to the population mean mu? Probably not. So because X bar does not equal mu. It could occasionally, but very, very unlikely. Statisticians recognized this and built and created an interesting way to estimate mu with the following. Mu equals X bar, sample mean that you got, plus or minus a little bit. Put that in quotations. Okay, so we're going to add and take off a little bit. So we have a range of values above and below the sample mean where the population mean might be. And then added a probability of being correct. This plus or minus a little bit accounts for an estimate of the size of this error due to sampling. That's what it's related to. And here is the formula for the confidence interval for means. So this is the population mean. This is sample mean. And this is a calculation of plus or minus a little bit. Hopefully it's a little bit. You don't want it to be too large. So you're adding a little bit on top and subtracting a little bit below. And so each of these, t-score, you look up in the t-tables. Sample standard deviation, so that's the standard deviation calculated from the sample, and the sample size. And this bit is a standard error. What is it for? It aims to capture the population mean, mu, in a range. Once you solve for the unknowns meaning t, s, square root of n, you have X bar already, you will get a statement like the following. We're 95% confident that mu equals 167 centimeters. Remember, this is where we're measuring height, plus or minus, and this is a little bit, or plus or minus error. This is a little extra stuff, how much we're off from the true mean. Or the 95% confidence interval for height is between these two values. So I've added a little bit on top to get 171.5. I've subtracted a little bit from 167 to get 162.5. So I'm 95% confidence that mean is somewhere in this range.